بسم الله الرحمن الرحيم. طيب, for tonight's lecture, we are going to implement a circuit that calculates the length of the hypotenuse in a right triangle, okay, given its other legs. You know that this is the hypotenuse, okay, and this is leg A, for example, and this is leg B. How do you calculate it? What is the length here? It is the square root of A square plus B square. So our circuit will take as input A and B, okay, and produce H, okay. So the input will be, in addition to go, of course, there is A and B, yeah, but we don't use A and B, we use data N for both, okay, data N for both A and B, okay. We take them in 2 consecutive clock cycles, and then output is going to be what? Shabab, from your experience, output is ready?
Should be H.
Yeah, and data out, yeah? Isn't it? Data out, which is H, basically, okay? Fine. Now, step number 1, what do? I set ready to 0 because last time, by the way, I in one of the previous classes, I told you that ready serves 2 purposes, okay? It serves one purpose, that the data is ready. That's the normal purpose that we are aware of. And the other purpose is to tell you that the circuit is ready to consume your input. And I stand corrected now and take my word back, okay? I am going to use ready only for alerting whoever is using the circuit that my output is ready, okay? My output is ready. So it's ready. It's not the job of the ready signal to tell whether the circuit is ready to consume input or not, okay? So the circuit will be ready to consume input if it is at step 2, okay? This is the for simplicity. We're just simplifying our circuit and our design. If it is at step 2, then the circuit will be looking for a positive edge on go, okay? Positive edge on go. So we have to wait here for positive edge on go, edge on go, and then let me call this step 2.5, okay, because it's basically at exactly the positive edge. During the positive edge, okay, I can also assign my register A the value of data N, yeah. And also, I want to set ready to be 0, okay? Because my data isn't ready yet, okay? Now, at step 3, I will say wait. Again, it's the same thing. Wait for a positive edge on go, yeah? And then at 3.5, what do? I read B, DN. All right? Right. Now I read B and A, and I think I'm ready now to calculate H. Okay, I'm ready to calculate H. So I can say at step 4 now, I can say my H, which is D out now in this case, D out is going to be equal to what? To the square root of A squared plus B squared, okay? But this is a very high level, right? Very high level for hardware. Okay, so we want to break down this. Remember, we want to make our algorithm suitable for hardware implementation. Now, for this, we are going to assume that we have another component, and we do have another component called the square root. Okay, it takes another go and it takes another dn. Okay, from outside, these signals, we'll call them what? We'll call them square root go and square root dn. Okay, to distinguish them, from square root from go and data in. Also, we'll have square root ready. Yeah, square root ready and square root d out. Yeah. This is from inside, it is still ready and d out. Okay, so what happens here is that we can actually calculate the input to the square root module, which is we can have like a variable called square root dn is equal to what? Actually, that's no, actually, we have to provide a positive edge on square root of go before providing the square root dn, right? So first of all, we have to initialize the square root of go. We can actually initialize it here, yeah? Can initialize it in this step. Square root go is 0 here, and here square root go is 1, right? And at the same time, I will set my square root dn to be what? To be a squared plus b squared. Now, this is a register that is connected to dn input of the square root function. Okay. Now I need to wait for what? Wait. I can say wait for square root ready to be what? To be 1. Yeah. Once it is 1, I know that my d out is actually what? Is this square root d out, yeah? And my ready is 1. All right? Yeah? And then at step 7, or even at step 6, I can just right away go to 2. Got it, Shabab? This is an algorithm for calculating the hypotenuse, the length of the hypotenuse. This side of the triangle, a right triangle, okay? Given its legs, other legs, the A and B, okay? Adjacent and the side of the right triangle. Do you understand the algorithm now, Shabab? Do you understand?
Yes.
Algorithm? Okay, great. Can you convert it to what we call ASM chart? Can you convert it to ASM chart? Can you help me with that? Probably. Let me just try to. Yeah, what do you think the ASM chart looks like? Yes.
Can I ask a question, Doctor?
Yeah, sure.
2.5 and 3.5. What is this exactly?
It's just the next step. Yeah, it's just the next step and you can call them three. بس أنا يعني it's like because why? Because I'm waiting for the positive edge, and because this is related to this, I called it 2.5. Step
Yeah,
two.
so it is next clock cycle.
Actually, it is. This one is going to be a melee assignment. A melee assignment with go going to 1. Okay, we are going to have a melee assignment of A going to the N, as we will see. Okay. So
Okay.
first, in the first, what we call state, what do we have here? State 0. This is reset. Okay. We have more assignment ready is 0, right? Yeah, this is nothing but step number 1. Okay, and then in step number 2, I'm going to have a state here. It is 1, okay, and I'm going to check for we have to have a state for that. I don't think we actually have to have a state. Okay, you can actually now we have to have a state actually. I will tell you what, we have to have a state because we are going back to step number 2. Okay, we want to go back to step number 2 in step number 6 without setting ready to 0. Okay, so we have to have a new state here, S1. And in this new state, only thing that we do is to check go. And if go is 1, I just forgot to add. I just forgot to add a check on go here as well. Remember, we have two situations in which go is either initially 0 or 1. Okay, and this will be different. Okay, will be different depending on the value of go. So if go is 0, then if go is 1, then you are going to actually wait for it to go to 0, right? This is 1. So this is this one, right? So in this step here, you are going to stay here. This is go again, as long as go is 1. All right. And if go is goes to 0 in here, then you go to status 2. Okay. And then again, you wait for go to go to 1. This is where the positive edge of go is received here. Okay, so now this is when you have go initially a 1, because you already missed the positive edge, so you have to go go has to go to 0 first and then to 1. All right. If go was 0 from the beginning, then we just skip this and go here right away. Okay, because if go is 0, then all it takes for a positive edge is for go to go to 1. Yeah, so this is exactly what I mean by this. Do you get that, ya shabab? If you have a question, please ask. It is important that
Clear.
Clear. Okay. طيب, why do I have a decision box here? Can you tell me why?
If we have 0 from the first, if it was 0, so if we don't have this box, when the clock is 0, we do not get benefit of that. We wait until it will be 1.
Yeah, you're not talking about the clock. We're talking about go itself. The signal go. Okay, the signal, we are trying to detect a positive edge on go. Here, this
Yes.
decision box differentiates between this scenario. Go here is 1, initially is 1. Okay, so in order to have a positive edge on go, you need to actually go, you need go to 0 first, and then go to 1. So this requires 2 states. Okay, and this is why we are, if go is 1, okay, then we are going to through this state and then this state, and then you detect a positive edge or not. Okay. However, the other scenario is when go is 0 to begin with. Okay, if go is 0, then all it takes is just one transition to 1. So in this case, if go is 0, okay, then you just skip this state that basically accounts for this transition. Okay, skip this state here and go straight to this state where you are waiting for go to actually go to a 1, and then you basically have a mealy box here that reads what? That reads A. All right, in the same state, then you are reading A in the same state. And I have seen a raised hand in a minute ago. Was there a question about this, Shabab?
No, it was me. I was gonna answer.
Does the answer make sense, yeah, Muhammad? Do you want to add something?
No. You just said what I was gonna say. So
Excellent, excellent. Okay. طيب, next, what do we have now? Next. So we need to create a new state, right? Because now at this state S3, we know that we read A. A has its value from the N, right? Now we want to read what? B, okay? Okay, so for reliability reasons, we can also all right, we can also so look at the transition here. The transition here happens when go is 1, right? So there is no way for go to be 0 when you enter this state, unless it changes in a super fast manner. And in this case, you may have a metastable condition, which is not allowed. Okay, so the default behavior is that go is going to be 1 for the next what? State. All right, so you are expecting this scenario. So in order to detect the next edge of go, next positive edge of go, you need to have a negative edge followed by a positive edge. So you have to have 2 states. Okay, have to have 2 states. All right, so we have to first detect a transition to 0. If I get a 1, I'll stay here. And if I get a 0, then I will go to S4, okay? And in S4, now I detect what? I detect transition to a 1, which is a positive edge on go. And as long as this is a 0, I will stay here. Otherwise, I will go this way now. I can read what? Read my B from the N. All right. And now I can go to a state where I will do what? I will do this step here, which is step number 4. You see, step number 4 is basically I'm setting what? I'm setting this register, okay, and setting this register. Actually, I can set them together with this mealy assignment. I don't need to wait for the next state. So I can say square go is this possible? No, I cannot do that. Why can't I do that, Shabab?
Because B is not loaded yet.
Yes, excellent. Yes, but note that I have control over square because the square root now expects a positive edge on goal, right? So I'm going to set goal at least to 0 here, okay? And then in here, I'm going to set now at this state, which is S5, I'm going to set square goal to be 1. Now this is a positive edge on goal, right? And also my square data n is going to be, yeah, my square data n is going to be, that's a long one, but yeah, A times A plus B times B, okay? All right, and then what do I do here? What do I do here, Shabab? I check for square root ready, yeah? All right, and if that is a 0, then I get back here to this state, stay in this state. Otherwise, what do I do? What do I do? Basically, my D out, what is that? Sorry for that. My D out, the mealy assignment. D out is what? Square root.
Square root D out.
Yeah. All right, and what? My ready as well is 1, yeah? Isn't it? My ready is 1, and then where do I go next? I go to S1 or S2, which one? Depends on, it depends on
Go.
Go.
yeah? It depends on go now.
Yes.
If go is 0, then if go is 0, then I go to S2. If go is 1, then I go to, then I go to S1. Got it, Shabab? Huh. Any question about it? Now, do you have, is it easy for you to translate this ASM chart to Verilog, Shabab?
I think it's easy.
Straightforward, huh?
Yes.
Yeah, the main reason for the assignment, Shabab, is to expose you to this. I want you to try to practice this, yeah? Practice writing an ASM chart and writing an algorithm first, and then algorithm is written for you, of course. But deriving the ASM chart and also trying to make it as efficient as possible. يعني هنا مثلا يا شباب I was about to create another state here, but I decided to have a mealy assignment instead. Why? Because I'm saving one state, yeah? And saving one state means this is one clock cycle less, yeah? One clock cycle less. So my code will have less clock cycle than if I use another state for the assignment. Okay, so remember that in the homework, you are also accounted for the clock cycles, the number of clock cycles. So whoever is getting of course, assuming the code is functionally correct first, okay? If the code is functionally correct, then we look at the latency, so I'll rank you by the least latency gets full mark with respect to the latency, and then each one will be ranked according to his latency. Okay. So it's like a leaderboard or something like that. Okay, it is going to be fun. All right. طيب. Any question before we switch to Verilog now? طيب. Let me switch to Verilog. Maybe I'll create another video. Just stop recording now and start another video so that this video doesn't become very long. Okay, stop recording.